I wish to start from the word resonance. Okay? So in senior 3 there, when you were told waves, there's one reached and looked at resonance. What is resonance? What is it? Resonance. Resonance. So we say resonance, okay, is the vibration of a body or a system at its natural frequency due to the impulses received from a nearby body vibrating at the same frequency. That's what we call resonance. Okay, say is a condition obtained when a body is said to vibrate at its natural frequency due to impulses received from a body vibrating from the same vibrating at the same frequency. Then application of resonance. Where do we find applications? We have two applications: determining the velocity of sound in the air, tuning musical instruments. Determining the velocity of sound in the air and then tuning musical instruments. Hazards. What is the disadvantage of resonance? Resonance leads to collapse of bridges, structures, buildings, etc. due to earthquakes. Of course, you know when earthquake occurs, you know the vibrations can cause the earth's crust itself to split, creating heavy and large cracks, or it can make even buildings to collapse, structures can collapse, bridges can collapse. So the hazards of resonance leads to collapse of buildings, structures, bridges due to earthquakes. Then we shall go to sound waves. Sound waves. Here I'm just going to explain as you, I hope you write. Sound is a mechanical vibration whose frequency lies within the audible range. Okay, say sound is a form of energy that enables hearing. The form of energy that is produced by vibrating objects. Sound is a form of energy that is produced by vibrating objects. Okay? So, sound waves propagate in air in series of compression and rarefaction because sound is a longitudinal wave. Therefore, it is characterized by the series of rarefactions and compressions. So when it is vibrating in the air, it vibrates in that way. There is when particles are overcrowded and when the particles are further apart. Okay? Now, because of that, we shall say explain why sound is regarded as an adiabatic change. Adiabatic change or process. Why sound is regarded as adiabatic change or process. Now, in the paper 1 hit, we talk about the changes in systems whereby we may have changes or processes which occur at constant temperature, others occur when the temperature is not constant. So adiabatic is one of them, whereby it is a process that occurs when heat is not allowed to enter the system or leave the system. There is no drop of temperature and there is no increase in temperature. That system, we call it adiabatic. Therefore, so how do we explain? Point number 1, we shall now say sound waves propagate in air. No, the first point we say sound is a longitudinal wave. That's number 1. Number 2, sound waves propagate in air in a series of compressions and rarefactions. By series of compressions and rarefactions. Then, next point, in compressions, temperature of air rises. In compressions, temperature of air rises unless heat is removed. Next point, in rarefaction, there is a decrease in temperature unless if heat is injected. Then conclude. The compressions and rarefactions occur so fast that heat does not enter or leave the wave. Hence, the process is adiabatic. So, when they are asking you to explain why it is regarded as adiabatic, now we expect you to tell us it is a longitudinal wave. That's one. Two, it vibrates in air or propagates in air by a series of rarefaction and compression. Next point tells us that in compression, temperature would increase, or the temperature is expected to increase. Okay, in compression, unless heat is withdrawn. Then in rarefaction, the temperature decreases unless heat is injected in. Then you conclude that the compressions and rarefactions occur so fast that heat is not allowed to leave or enter the wave. Hence, adiabatic process. That's it. Then we look at characteristics of musical notes. Characteristics of musical what? Notes. Characteristics of musical what? Musical. Musical notes differ in pitch, loudness, and pitch. Loudness and then quality, which we call timbre, like that. So, pitch now. Let's write something about pitch. How does pitch differ? How does pitch, affect the musical notes? Okay, so we shall say the pitch is the characteristic of sound by which the ear assigns a place on a musical scale. Anyway, pitch depends on the frequency of vibration. Pitch depends on the frequency of vibration. Depends on the frequency of vibration of sound waves, i.e., it increases as the frequency of sound increases. So then we go to loudness. What about loudness? Loudness is the amount of sound energy entering ear per second. Amount of energy entering ear per second. Okay, take note of that. Okay. Then we shall go to quality. Quality or timbre. In timbre here, what does it mean? Enables us to distinguish between two notes. Enables us to distinguish between two notes of sound having the same loudness and pitch. Timbre depends on the number of overtone or harmonics present, which depends on the amplitude of the note. And yes, amplitude of the note. Then let us go and look at this one. What are the factors affecting loudness? Loudness, we said, it's amount of sound entering ear per second. The factors we have two: sound intensity and amplitude. Factors which affect the loudness, we look at intensity of the sound and the amplitude of the sound wave. Then from there, I'm just talking about those ones because I'm expecting you to have studied them in senior 3. Then let us go and look at echoes. This is reflected what? From hard surface, from hard what? From hard what? Surface. And you shall say. Then after that we look at it, reverberation. Reverberation. What is reverberation? We shall say reverberation is prolonged sound, is an effect, that occurs when echo joins the original sound. The echo joins the original sound to produce prolonged sound. Prolonged sound. What's the spelling of prolonged sound? To produce the prolonged what? Prolonged sound. Prolonged what? Sound. Then implications. What are the implications of echoes? Implications of reverberation or echoes. Of reverberation. There are two implications. Okay. The first one we shall say increases or enhances. Increases audibility. Increases audibility of sound. Increases audibility of what? Of sound. Then the next implication. So this is advantage. The next implication we say too much reverberation. Too much reverberation causes confusion in speeches. Causes what? Confusion in what? In speeches. Then we say, note, it is minimized in large halls or cinema halls. By using soft what? Soft bodies or soft carpets. Soft bodies or soft carpets. By using soft what? Carpets. Okay? By using soft carpets. Or by lining the inside wall of the room with sound absorbing material, usually made of soft material. Then there is a question here which I say. A question which says, explain why reverberation is necessary while making speech. Explain why reverberation is necessary while making speech. So what do you say? Too short reverberation time makes a room sound dead. Too much reverberation makes a room sound dead. But if it is too long, if the time is too long, confusion results. Confusion will occur. For speeches, half a second is acceptable. Reverberation time is made the same irrespective of the size of the audience. Okay? By lining the walls with soft material so that there is a reduced reflection on sound. Next question is, explain why echoes are not heard in small rooms. Echoes are not heard in small what? In small rooms. Echoes are not heard in small rooms. Okay? So here what do we say? An echo to be differentiated from its original sound, there must be, okay, we can say an echo to be differentiated from its original sound. There must be a minimum time lag of at least 0.1 second. 0.1 what? Second. Okay? Between the original sound and echo. Between the what? The original sound and echo. Original sound. Original sound and what? And echo. That is it. Therefore, in small rooms, the time lag is less than that. Therefore, in small rooms, time lag is less than 0.1 seconds. Hence, echoes cannot be heard. Is that clear? So we talk of time. There must be a minimum time lag of 0.1 what? Seconds. And I say that in small rooms, the time is less than that. Therefore, echoes cannot be heard. Is that okay? Then we go to reflection of sound. Reflection of what? Sound. Briefly, we talk about reflection of sound. Of course, by definition, we shall say this is the change in the speed of sound waves as they move from one medium to another of different optical densities. Okay, of different optical densities. So we say is a change. Is that change in speed of sound waves as they travel from one medium to another of different optical densities. Question. Explain why sound is louder at night. Explain why sound is louder at night. Than during the day. Very simple question. This is about the medium. Because at night, talk about what happens to the air, the density of air and the density of air during the day. So during night, the density of air is cool, therefore the density of air is high. During the day, the air is warm, therefore the density of air is very hot, is less. So meaning that during the day, the air near the Earth's surface is warm, okay, and therefore becomes less hot, dense. So sound is propagating from a less dense medium, okay, to a more dense medium. Therefore, it bends away from Earth's surface. During the night, the air near Earth's surface is cool, therefore more dense. So sound is propagating from a more dense medium to a less dense medium. Therefore, it is reflected towards Earth's surface. So what do we say? We say at night, the air in the atmosphere near the Earth's surface is denser than the one above the Earth's surface, than the one above it. Sound produced in lower air is totally internally reflected within the lower, more dense air without wastage. So in other words, for us we can say that at night, air near the Earth's surface. Earth's what? Surface is cool and hence more dense. Then next, the sound propagates from a more hence medium. Let's say medium to arrest this. Hence, totally internally reflected. To the Earth's surface. The Earth's what? Surface. Hence more rounder. Hence more what? Next tell us, you did it. Using the what? The day comma. What happens? Air is warm near Earth's surface. Is warm. Hence, this. And sound is reflected away. Is reflected away from the Earth's surface. The Earth is what? Surface. Hence, let's what? Let's listen loud. Then, next we look at, of course, let's look at interference of sound. Look at interference of what? Sound. Look at interference of sound. Interference of what? Sound. Now, in interference of sound, of course, we shall say interference of sound waves is the superposition of waves from different to coherent sources, resulting into alternate regions of maxima and minima intensity. Resulting into regions of maxima and minima intensity. Of course, when we say maxima, that is when we talk of constructive interference. Minima, that's minimum intensity of sound, and maximum intensity of what? Sound. So when the sound waves from two different coherent sources, coherent sources are sources of sound which produce waves of the same amplitude, similar amplitude, frequency, and wavelength. So when there are two different coherent sources and they produce sound, there is superposition of sound waves producing regions of loud sound and soft sound. So loud sound is maxima intensity, low sound, that is minima intensity. So then we look at experiment to show interference of sound. Experiment to show interference of sound. So we are going to draw a tube. We have a tube here. Another one is here. That's a tube. Then we draw another tube here. So we have these tubes, we have the source of sound here, and we have the observer here. The observer, we have tube A and B. This is A, this is B. So we're going to write to explain how interference can be observed. Because now you're going to hear region of maxima and minima in terms of sound. So we shall say tube A is fixed. Tube A is what? Fixed. That's point number one. Tube A is fixed. While B is free to move. Is it okay? Tube A is fixed, while B is free to move. That's number one. Next statement we say, next point we say, a note is sounded at S. A note is sounded at S, and it is detected at E. A note is sounded at S and it is detected at E. The next point we say, tube B is then pulled out slowly. Tube B is then pulled out what? Slowly. It is noted that, now that's observation now. It is noted that the sound detected at E, it is not, that's an expression, it is noted that sound detected at E increases to maximum and reduces to minimum intensity at equal intervals of length of the tube. At equal intervals of length of the tube. Next point, conclusion. The alternate maximum and minimum intensity of sound are interference patterns. Is it okay now? I hope you find it very interesting. So this one is fixed, this is moving. A note is sounded here, detected here. This one is pulled out slowly. It is observed that at E that loud sound or the sound, the note which is detected at E, the sound increases to maximum and minimum at equal intervals of length of the tube. So the alternate maximum and minimum intensity of sound, okay? The alternate maximum and minimum intensity of sound, okay, is what we call interference patterns. Interference what? Patterns. Then we look at measurement of velocity of sound in air by interference. Velocity of sound in air by interference. By what? By interference. So we are going to have, let me say, here we have okay, then that is the microphone. Then you can say it's connected to. Then here we shall have this one here. Then here we have another one. But then this one is connected to, it is connected to a circle. There is a circle here. CRO what? CRO. Don't know whether I see it. CRO. Then here we shall have. This is N. Then here we have A. We have B. And in the distance here we shall call it lambda over 2. From here to here, we shall call it lambda over 2. So then here, yeah, A and B. And this is audio frequency oscillator. Audio frequency oscillator. Audio frequency what? Oscillator. So that's the audio frequency oscillator. And then we have loudspeaker. So there is loudspeaker. This is loudspeaker. This is the loud what? Loudspeaker. Okay? Loudspeaker. Then we have vertical board. This one is the board. This is it. This is the board. So we shall say the microphone is positioned in front of N. The microphone is positioned. Now the first statement we shall say the microphone is positioned in front of board N and connected to Y plate of CRO and connected to Y plate of the CRO. So this microphone, now we shall have microphone. Okay, I think let us use this one. Is we have here loudspeaker out here. This loudspeaker here. So this is a microphone now. Microphone is positioned in front of what? N. So this is a microphone positioned in front of N and it is connected to the Y plate of CRO. Next point. The microphone is moved back from N towards L. The microphone is moved from N towards L. L is here. This is speaker. The microphone is moved from N back towards L. Towards what? Towards L. The amplitude of the wave seen on a CRO increases to maximum value when the microphone is at the position B. When the microphone is at the position what? B. You get it? So you move it from here back towards what? The loudspeaker. And then you say that it is observed that the amplitude increases to maximum value on the CRO when it is moved towards here, maybe at position what? B. So we say the amplitude of the waveform seen on the CRO increases to a maximum value at a position say B. This is antinode. This is antinode of stationary wave form. This is antinode of stationary wave form. Of course, you know in a stationary wave, there is this one. The amplitude is what? Is maximum. Okay, that's antinode. Then next point. The microphone is again moved towards L until the amplitude reduces until the amplitude increases to maximum again. The microphone is further moved towards L, okay, until the amplitude again increases to maximum, say at A. At what A? So this is a position of antinode. And you know that the distance between two antinodes is what? The distance between two antinodes, this distance is lambda over 2. So we shall now say the distance between A and B is measured and recorded, and this is lambda over 2. So we are saying the distance AB is measured. The microphone is further moved towards L and several maxima located. The average distance D between the successive maxima is calculated. So we are saying that the first thing is move the microphone is moved away from N until the waveform, the amplitude increases to maximum. Then you note this position. Then it is again moved toward the side away from N until the amplitude again increases to maximum. That is the position of the second antinode. Then you can again move, okay, until you get several maximum amplitude positions, and then after that you measure the distances between two successive points. Then after that you get the average, which will be lambda over this average D, which will become lambda over 2. Then after that we say, knowing the frequency of the note from the loudspeaker, the loudspeaker, the speed V can be calculated from V is equal to F lambda. But our lambda is 2D, so it will be V equals 2FD. Yeah. So that's how. So when you're writing, the point number 1 we say the microphone is positioned in front of board N and connected to the Y plate of CRO. The microphone, next point, the microphone is moved from N towards L loudspeaker. Next point, the amplitude of wave form seen on the CRO screen increases to maximum value, say at B. The microphone is further moved towards L until the waveform, amplitude of waveform increases to maximum again. say at what? At position A. The distance between AB is measured and recorded. The microphone is further moved towards L and several maxima located. The average distance D between successive maxima is calculated. Then D equals lambda over 2, implying that lambda equals 2D. Knowing the frequency of the audio oscillator, the speed can be obtained from 2FD. That one is done. Then the next one is the measurement of loss of sound by Quincke's cube experiment. Measurement of loss of sound by Quincke's cube experiment. So let's draw that tube. So this tube, we are going to have a tube there. This tube, okay, and then we have another tube here. Okay, it's a tube. This is the tube. So here, so here we shall have the note sound. Here we have ear, can call it that. Then we shall have here we have something here. We have that, okay. And we call this one P, and then we should also have this. And we call this one M. And then the distance between the two, we shall call it K. Okay, this is a P, this is a Q, this is M, this is N. So we have this is a tube what? That's a tube what? B. This is movable. This one is almost the same as the first one for interference, but this time we are going to get the speed of sound using Quincke's what? Tube. So in this one we are going to say a source is placed at S. A source is placed at what? At S, okay? And a note produced is detected at A. Next point. A wave travels around the tube in a direction S. I think I suppose we'll have direction, SAB. In a direction SAE. In the direction SAE. This is A is here. In the direction SAE. Okay? So then after that, next point. While another travels in the opposite direction, SBE. So they are saying that not sounded here, detected here. Okay, a wave travels around the tube in the direction of SAE, and another in the direction SBE. Since all these waves are from the same source, therefore they are coherent. Because they are from the same source, therefore they are what? They are coherent. The next point you say, side B of the tube is then pulled out slowly, thus making SAE, that's making SAE, and SBE of different length. Of different what? Length. When SAE and SBE are equal in length, the observer hears a loud sound. Next point, of course, we know when they are equal length, that means the observer will hear a loud sound. That's constructive interference. The two will have covered the same distances. So we say, as next point, as B is pulled out, the sound dies away and becomes minimum. As B is pulled out, sound dies away and it becomes minimum. The path difference, SBE, the path difference, SBE, minus, that is the difference in the length the waves will travel, minus SAE is equal to this one, the path difference, normally it is lambda over T, normally lambda over T over 2, is lambda over 2. Then next, and the waves are out of phase, and these waves are out of the first the path difference. The path difference, this is the path difference. Path difference is equal to this, and waves are out of phase. And waves are out of what? Out of phase. So now this is the difference in the distances moved. The waves are out of phase. Next point says, if the tube is pulled further, the sound increases to maximum. If the tube if the tube is pulled further, the sound increases to maximum. So that's the constructive interference. No? So the sound increases to maximum. If K is the distance moved from M to P2, okay, then we shall now say that our distance K, then K is equal to lambda over 2, so that means our lambda is 2K. Our lambda is 2K. If the frequency of the note is known, then the speed of sound can be obtained from F lambda, which is 2F. I think it is not so much different from the previous one. It is not so much different from the previous one. So here it's all about sounding the note here, and then detecting, and then the sound traveling around the tube here and there, okay, and then pulling out to this tube slowly until the sound increases to maximum, and until when the sound increases to maximum. So the sound increases to maximum, and I'll put it from here to here. Then you measure the distance between the two, okay, and again you continue pulling until it goes to maximum sound and minimum sound. Then measure this distance. Of course, I told you that this one is position of note. So if it is maximum sound, this is antinote, this is antinote. If it is minimum sound, this is note, this is note. But the distance between note and note, antinote and antinote, is lambda over 2. So this distance is lambda over 2. So knowing the frequency of the oscillator here, of the note, then you can be able to get the speed of sound. Okay? Okay, so for this one, we'll stop there.